Hello, welcome to my heat transfer video assignment. My name is Jason. In this video, we'll be going over a boiling convection problem. So let's get started. So here's the question. Consider a pool of saturated water at atmospheric pressure. The base of the pool is made of thick, polished copper. So here's a schematic. To generate steam, exhaust gas is flown underneath parallel to the base plate with a velocity of 3 meters per second at an average temperature of 1090. So here we go. The bottom of the surface plate is at constant temperature of 110. Use the properties of air for the exhaust gas. And so part A, determine the boiling heat transfer rate. So our assumptions, the standard assumption, so steady state neglect radiation and constant thermal properties. We're also going to assume saturated and nucleic boiling. We'll assume ideal gas behavior, and we'll assume the environment is at 1 atmosphere for the exhaust gas. So in this problem, there's heat transfer from convection below from the exhaust gas, then there's conduction through the thick plate, and then there's boiling, again, another form of convection. So our thermal circuit looks like this, where we have 3 sets of resistance added in series. And because they're in series, the heat transfer rate for all 3 of them are the same, from convection to conduction to boiling. In the question, they're curious about the boiling. So if we solve for either the conduction or convection, we'll get the heat transfer for also boiling. So we're going to go with convection to find the boiling. And this is the equation we're going to use to find the convection outside. So first, we're going to start by analyzing the area below the plate. And this is just external flow over a flat parallel plate. So we'll take our properties at our film temperature, which is just the average between the surface temperature and the air temperature. So that's 600 degrees, and we'll get our properties at 600 degrees. And then we'll calculate the Reynolds number. In this case, it's laminar. So we'll go to our correlations table, and we'll pick out the one that says for laminar. Note that this is the average Nusselt number. Also, just to note that we satisfy the conditions to use it. Our Prandtl number is greater than 0.6, and our Reynolds number is less than 50,000. So now we can sub in our values into that Nusselt equation. So we get a value of 104.8. We can use this to solve for our external convection factor, our H value. And so this is our value for forced convection. We're also going to check for natural convection to see if it's present. To start off, we'll calculate the Grashof number using this equation. Just note that this L value, we're going to be using the corrected length value, which is just the area of the plate divided by its perimeter. So subbing in our values, we get a Grashof number of 1.98 times 10 to the 7. We can take the ratio of the Grashof number with the Reynolds number, and this is the value we get. This value is a lot smaller than 0.1, so natural convection can be neglected. We'll just only look at forced convection here. So now we can just plug in our forced convection value and plug it back into this equation. So we get a heat flux of 6,252. If we multiply this by the area, and in our case, our area is just 1, we get the heat transfer rate. And so that's just the same value, but this time it's in watts. And so this is our answer to part A, which was to determine the boiling heat transfer rate. Moving on to part B, determine the temperature of the top surface of the plate, comment on the results. So to do this, we'll just use this boiling equation we have from class. So we just solved for Q. So we're going to get our water properties at 1 atmospheric. These are just standard to look up through a table. The only 2 new values here are this surface tension and this surface finish values. And for those, we can just get those from 2 separate tables. Our saturation temperature is 100, and our surface is water to copper polished. Yeah, so we can just plug in all our values into the equation. We get a wall temperature of 103.6. So just some comments on this. 103.6 is larger than our saturation temperature, so it is over 100 degrees, which is what we'd expect. However, this is not in the range of nucleic boiling. This is actually in the range of natural convection. So our earlier assumption wasn't valid here, but that's the approach we had to use. Moving on to part C, examine the impact of your assumptions on your solution. What would change if your assumptions were not valid? So for this, I'm just going to neglect the 3 assumptions of steady state and constant thermal properties and ideal gas behavior. These are outside the scope of the course. If we couldn't make these assumptions, then I'm sure we would have to do some integration, and our process would be a lot more complicated. Looking at neglecting radiation, if that assumption wasn't valid, then we would have to add an extra heat transfer rate. This would be added in parallel to our heating surface. If we were to neglect our nucleic boiling assumption, then we would have to use a different formula. We couldn't use the one that we used earlier. And lastly, if we couldn't assume that the environment was at 1 atmospheric pressure, then we would have to retrieve our water property values at saturation temperature. And this also applies for the heating gas. Thank you for your time and attention. Have a nice day.